Hello there, this is a follow-up or continuation of my previous video in which I tried to explain what implicit differentiation is and how it works. And in this video, I'm just going to be showing you a couple more examples to help you get the hang of how implicit differentiation works. So, first example for this video, find the slope of the tangent line to the curve x cubed plus y cubed equals 3xy at the point where x and y are both 3/2. Well, looking at the graph, kind of looks like at that point the tangent line would be going sort of like this. It would have a slope of maybe -1. Well, let's work it out and see if that's what it actually turns out to be. So, I'm going to start by taking my equation, which I wouldn't want to try to solve that for y. That would get complicated. But I don't have to. I can just leave it the way it is and differentiate both sides with respect to x. So I'm thinking of x as the independent variable, and then y depends on x. So this equation implicitly gives me y as a function of x. So, following all the rules for derivatives, the derivative of a sum is a sum of the derivatives. The derivative of x to the 3 power would be 3 times x to the 2 power. And the derivative of something to the 3 power would be 3 times the something to the 2 power times the derivative of the something. So I'm using the power rule there with the chain rule. On the other side, to find the derivative of 3xy, that is a product, it's got things multiplied together. So I'm going to use the product rule. I'm going to think of it as a 3x times a y. So the 3x gets multiplied by the derivative of the y, and the y gets multiplied by the derivative of the 3x. So we've got 3x times the derivative of y, dy dx, plus the derivative of 3x, which is just 3, times y itself. So now I'm done differentiating. Let me solve this for dy dx. Get it in the form dy dx equals whatever. So right now I've got two terms on the left, two terms on the right. On each side there's one term that does involve dy dx and one that does not. I want to get it so that both of the terms that do involve dy dx are together on one side of the equation, and then the other terms that don't involve dy dx are on the other side. And since everything has a factor of 3, I might as well just go ahead and divide both sides of the equation by 3, make things a little simpler. Now, I've left the y squared dy dx where it is, but I've subtracted x dy dx on both sides. And then over on the right, I've left the y where it is, but I have subtracted x squared on both sides. So now on the left, I've got both my dy dx terms, and I'm going to factor out the dy dx. So it's dy dx times y squared minus x equals y minus x squared. And when I've got dy dx times something else, and I want just dy dx by itself, I can get that by dividing both sides by the something else. In this case, by the y squared minus x. So dy dx equals y minus x squared over y squared minus x. Now remember, we wanted this at the point 3/2, 3/2. So I got to take those numbers and plug them in for x and y. And really, I could have plugged in the numbers up here right after that first step when I was done differentiating, or at any time in between. So if it's easier to put the numbers in here and just work with an equation that has numbers in it and the dy dx to solve for that, you could do it that way. But at some point, I've got to plug in 3/2 for x and 3/2 for y. And if I do that here, I get dy dx equals 3/2 minus 3/2 squared over 3/2 squared minus 3/2. Now, to simplify that down, you could either carefully plug it into a calculator or carefully work it out by hand, or in this case, a quick shortcut is to notice that the numerator and the denominator are opposites of one another. They're the same thing, only subtracted in the opposite order, like an a minus b over a b minus a, and so that reduces to just -1. So that is our answer. The slope of the tangent line at that point is -1, which matches what I thought it should be. Let's try one more example. Let's find dy dx for the equation y cosine x equals ln y plus x sine y. Now, I don't know where this equation might come up in any application or real-world context. I just kind of made it up for this example, but it does have kind of an interesting looking graph to it. And it mixes a few things together here. So, as always, we are going to not worry about trying to solve this equation for y. That would be a monster. But we are going to leave the equation the way it is and differentiate both sides with respect to x. So on the left, we have the derivative with respect to x of y times the cosine of x equals, on the right, we have the derivative with respect to x of ln y plus x sine y. To find the derivative of y times the cosine of x, we are going to need the product rule. That is, after all, a product. It's two things multiplied together. So we're going to have y times the derivative of cosine x plus the derivative of y times cosine x. And on the other side, that's going to be equal to the derivative of ln y plus, and here again, we're going to use the product rule. We're going to have x times the derivative of sine y plus the derivative of x times sine y. In each case, whenever we have the derivative of something, it's always the derivative with respect to x. So let's work out these individual derivatives. The derivative with respect to x of cosine x would be negative sine x. The derivative with respect to x of y would be dy dx. It would be the derivative of y with respect to x. The derivative of ln of y would be 1 over y times dy dx. Remember, the derivative of just ln of x would be 1 over x. So if you put that together with the chain rule, the derivative of ln of something is 1 over the something times the derivative of the something. So here that's 1 over y times the derivative of y. Plus we have x times, and now for the derivative of sine y, we got to use the chain rule here. The derivative of the sine of something is the cosine of that something times the derivative of the something. So here that would be cosine y times dy dx. And then we have the derivative of x, which is just 1 times the sine of y. Now, if we want this solved for dy dx, look at all the terms here and notice that some of those terms involve dy dx and some do not. And so I want to rearrange things so that on one side of the equation, we have all the terms that do involve dy dx. And on the other side, we have all the terms that do not involve dy dx. So I put it down as dy dx times the cosine of x minus dy dx times 1 over y minus dy dx times x times the cosine of y on the left side equals positive y times the sine of x plus the sine of y all on the right side. On the left side, I'm going to factor out that common factor of dy dx. So it's dy dx times the expression cosine x minus 1 over y minus x cosine y. And so that's equal to the right side, y sine x plus sine y. And now I'm going to divide both sides by that factor that's being multiplied by dy dx. So dy dx ends up being equal to y sine x plus sine y over cosine x minus 1 over y minus x cosine y. Now I can just stop there and say, okay, there's my expression for dy dx, but it might look a little nicer and a little less complex if we get rid of that fraction within fractions by multiplying the numerator and the denominator both through by y. So if I do that, I get dy dx equals y squared sine x plus y sine y over y cosine x minus 1 minus xy cosine y. So there's my answer. There's my dy dx. So where do we go from here? What does implicit differentiation help you with? Well, it leads to or prepares you for something that's called logarithmic differentiation, which is a way of more easily finding the derivative of some complex expression that involves products and or quotients and or powers that you could use the rules of logarithms to turn into something that's easier to differentiate. And it's often shown as sort of a preliminary or prerequisite to related rates problems, which is one big kind of application that you learn about in calculus. So those topics are beyond the scope of this particular video, but they're things that you often go on and study after you've learned about implicit differentiation. And if I feel like it, or if somebody asks me to, I might go ahead and make a video on one or both of those topics. But this is it for implicit differentiation. Thanks for watching. I hope this was helpful.